A very good morning to Dr. Shamsul and my dear friends. So today for INT504 project and presentation, I will present three of my journals. First will be high performance self-powered photodetectors based on perovskite and graphene. Second, three-dimensional graphene field effect transistor as performance detectors. And number three will be broadband black phosphorus photodetector with high responsivity. Next, the first journal will look into the high performance self-powered photodetectors based on perovskite and graphene. Okay, so I will summarize on this title, whereby in this article, Julian Lee had proposed a self-powered photodetector with a graphene electrode and a perovskite photoactive layer. The graphene layer, electrode, and the perovskite layer is prepared using a solution transfer process and solution coating process respectively. This makes the device low cost. Graphene can form a Schottky junction with TiO2 tin oxide to effectively separate or transport photogenerators excitons at the graphene or perovskite interface. The unique charge transport property of graphene and strong light absorption characteristic of perovskite allows the photodetector to have a broad range of detection from 260 to 900 nanometer and ultra high on-off ratio of 4 to the power of 6, rapid response of light on-off less than 5 milliseconds, and a high level of detection of 10 to the power of 11 joules. They have suggested a new method, self-powered photodetectors with high performance and low power consumption on a large scale. Next, I will further explain on the research methodology of this journal. First, device fabrication. FTO pattern by using zinc powder and diluted hydrochloric acid, which is used as cleaning with ultrasonic cleaner. The deposition. 40 nanometer tin oxide deposited onto FTO by using low temperature procedure. The third process will be cleaning the deposited substrate with deionized water and perform annealing. The annealing temperature is at 200 degrees Celsius, 300 degrees Celsius, and 450 degrees Celsius. Fourth, the first one is a multi-layer graphene transferred tin oxide, which is done through chemical vapor deposition method. Second, opposite side treated with UV zone. This UV zone, which interval is 1 minute, 2 minutes, 3 minutes, and 4 minutes. Next, perovskite solution coated on tin oxide, which is done by spin coating process at 4000 rpm for 45 seconds. For the sixth step, formation of the dark perovskite film is by annealing at temperature of 100 degrees Celsius for about 10 minutes. Next is also a spin coating process whereby PTAA solution mixed with perovskite solution and coated at RPM of 3000 for about 30 seconds. Once done, the analysis has been performed. There are few analyses performed on this research, whereby the first one is a Raman spectroscopy, second one will be photoluminance, third will be fission to determine the surface morphology, and the fourth one will be X-ray. Fifth one will be photoresponse characteristic by using a photometer analyzer attenuator used to tune the intensity of light for low light response measurement. And the last one will be IV characteristic, which is the IV curve. Next, I will further discuss on the result and the discussion. Okay, as shown in figure 1a, it presents the schematic diagram of a self-powered photodetector with a configuration of FTO, tin oxide, perovskite the tin oxide is deposited onto the FTO using a chemical bath approach, and graphene is transferred into the tin oxide using a solution process. This was observed at the FISM. Figure 1b, which is on the right hand side, shows the band structure of the photodetector in which a Schottky junction is formed between tin oxide and graphene. Under high illumination, excitons with low binding energy are generated in the perovskite film and dissociated into electrons and holes. Next, figure 1c and 1d shows the schematic band diagram of tin oxide, and the graphene before and after contact are depicted. Graphene shows a p-type property in the air, and the tin oxide is an n-type semiconductor. When they are in contact with each other, electrons are depleted from tin oxide, which alters the energy band to form an internal electric field that points from tin oxide to graphene, resulting in rectifying behavior. Next, this is the IV curve which obtained on the result. Figure 2a shows a current voltage IV curve between tin oxide and graphene is first measured in the dark. By sweeping the bias voltage from -1 to 1 volt, a nonlinear IV curve indicates that there is a Schottky junction resulting from a difference between the work function of graphene and the Fermi level of tin oxide. Figure 2b is the Raman spectra, which excited by a 532 nanometer laser of graphene in silicon oxide. In the structure of perovskite, graphene, tin oxide, PTAA, perovskite, graphene, tin oxide, the G and 2D, as shown in figure 2b, are the typical Raman peaks of graphene and are located at 5,584 and 2,697 centimeter, respectively. Figure 2c is to examine the characteristic of the transfer of charge between the different layers using PL squenching mechanism. Steady state PL is measured. The PL spectra as shown exhibit a peak of 767, resulting from the band-to-band recombination of the perovskite. Alright, figure 3a shows the cross-sectional SEM image of the self-powered photodetector with PTAA on the left side. Figure 3b and 3c is interestingly to note the perovskite film on the graphene shows a larger grain size than the tin oxide, which due to the hydrophobic properties of graphene. 3D shows the UV-Vis NII absorption spectra of photodetectors with and without PTAA. The devices show strong and broad absorptions in UV and visible regions. Next, the figure 4. The figure 4 shows the photoresponse behavior of the photodetectors studied under illumination of monochromatic 560 nanometer light with a power density of 40 milliwatt per centimeter square. With and without PTAA operated at bias voltage 1 volt and without bias voltage. It is found that the photodetector shows a photocurrent of 2 amp 0.2 milliamp under self-powered mode without adding any bias potential. The photocurrent can be improved to 0.6 milliamp after coating PTAA. The next figure, which is figure 4b, shows the UV-Vis NII absorption spectra of photodetectors with and without PTAA. The device shows strong and broad absorption in UV and visible regions. Figure 4c presents a temporal response of the photodetector during one pulse of the incident light. Figure 4d is the density of photodetector measured using Fourier transform spectrum analyzer. Next, we go to figure 5, which shows the photovoltaic performance of self-powered photodetectors. Is also measured under solar simulator illumination. When the perovskite is deposited on the graphene, the IV curve of the device exhibits a significant non-linear behavior in the dark, indicating that Schottky contact exists between tin oxide and graphene. Figure 5b shows the IV curve of the photodetector under solar simulator illumination at different light intensities. Figure 5c shows the characteristic result from the structure of photodetector. The photogenerated electrons are transferred to the tin oxide, leaving holes in the graphene. Under higher light illumination, more holes occur in the graphene. While Figure 5d presents the stability photodetectors, especially when it is composed of perovskite, which is sensitive to moisture under ambient condition. The result shows the time and cycle stability measurement have been carried out to evaluate the durability of the photodetector in the air. The performance of the photodetector after storage in air for 5, 10, and 20 days. The photocurrent indicates a negligible decay and mostly remains in its primary stage, which suggested long-term air stability of the photodetector. Table 1, as shown above, is summarized of the most important figures of merit of recently developed self-powered photodetectors. In general, the data of photodetectors based on graphene and perovskite are among the best, which indicate the super priority of our device used in photodetection application. Next, we'll look into the journal number 2, which is three-dimensional graphene field effect transistor as high-performance photodetectors. Okay, the summary of this paper. This research article proposed a self-rolled-up 3D GFET photodetector to balance its photoresponsivity, spectral range, and electrical bandwidth. The 3D GFET provides a natural resonant microactivity to enhance the optical field and increases the light-graphene interaction area. This results in significant enhancement in optical absorption and improvement in the photoresponsivity of the 3D GFET. This 3D GFET photodetectors demonstrated at the room temperature photodetection at ultraviolet, visible, mid-infrared, and terahertz regions, with both ultraviolet and visual photoresponsivities of more than 1 ampere per watt and photoresponsivity of 0.232 ampere per watt at 3.11 terahertz. The electrical bandwidth of these devices exceeded 1 MHz. This recombination of high photoresponsivity, a broad spectral range, and high speed will lead to new opportunities for 3D graphene optoelectronic devices and systems. Next, we will look into the research methodology. First, the aluminum layer is sputtered on a silicon tensile strain silicon nitride layer were deposited using a low frequency of 380 kHz and high frequency of 13.56 MHz. This was done under plasma enhanced chemical vapor deposition method (PECVD). Next, chromium and gold gate electrode structure was sputtered on the silicon nitride layer about 30 nanometer of thickness. This was done by using a sputtering technique. The third process, CVD grown graphene, was transferred onto silicon oxide layer and patterned using oxygen plasma etching. This was done under plasma etching method. The fourth process, evaporation of chromium, aluminum source and drain electrodes. This is to formation of 2D buried gate GFET. Then the next will be 2D GFET roll up process. This was done by etching aluminum sacrificial layer using VCLT solution. Next, 3D GFET formation is by washing and drying the stages and also load up the 2D buried gate GFET. This 3D GFET characterization process by spin coating at RPM of 3000 at 30 seconds. Once done, there are few analyses as be done First one will be Raman spectroscopy to determine the presence of graphene layer in the roll-up state. Second one, electrical parameter analysis by probing. Third one will be photocurrent experiment. Fourth one will be FEM or SEM. Then the last one will be RF characteristic by impulse response. Next, we will look into the results and discussion for this journal. The three-dimensional graphene field effect transistor as high-performance photodetectors. This figure 1 shows the structure and SEM images of the roll-up 3D GFETs. Figure 1a shows the 2D buried gate GFET formation after evaporation method, the first figure. Figure 2, figure 1b, it shows the formation of 3D GFET after washing and drying stages and also the roll-up process. Figure 1c, d, e, and f shows the magnified 3D GFET tube roll-up from 2D buried gate GFET which is taken under SEM. Next, the figure 2, which elaborates the electrical properties of GFET before 2D and after, which is 3D, the roll-up process. Figure 2 shows the electrical properties of GFET before, which is at the 2D condition, and also the after the roll-up process, which is the 3D process. The direct point of the 2D GFET, which is defined as the gate voltage Vg, at which the minimum drain source current is obtained, occurs at 6 volt, which indicates the graphene is p-doped. The direct point of 3D GFET, however, has shifted to 7 volt. This is the possible reason of the direct point shift is the absorption of water molecules from the etching solution used for the aluminum sacrificial layer in the roll-up process. Second figure, which is figure 2b, shows the output characteristic curve of the 2D GFET. With the increasing source drain voltage, the output source drain current ID increases linearly. At a specific VDS, the output current first decreases and then increases with increasing gate voltage from -1 to 11 volt, thus indicating good gate control ability. The third figure, which is figure 2c, shows the output characteristic curve of the 3D GFET. The output current of the 3D GFET is smaller than that of the 2D GFET under the same gate and source drain voltages. This phenomenon indicates that the GFET resistance increases after the roll-up process. Figure 3. It shows the photoresponses of the 2D GFETs and the 3D GFETs in ultraviolet and visible regions. Figure 3a shows the experimental setup of photoelectric properties of 3D GFETs in ultraviolet region at 325 nanometer were characterized and compared with those of reference 2D GFETs, which the same graphene conductive channel dimension. Figure 3b shows the laser power dependence of the photocurrent of a 3D GFETs with 2 windings and a reference 2D GFETs under 0 gate bias and 0 source drain bias. The 3D GFETs photocurrent rises linearly with increasing incident laser power. The responsivity, which defines as a ratio of the measured photocurrent of the input laser, is 2.3 milliamp per watt. The responsivity of 3 orders of magnitude higher than the reference 2D GFET, which is 1.6 microampere per watt. Figure 3.3c shows the gate voltage dependent photoresponsivity of the 3D GFETs under 325 nanometer laser excitation. The photoresponsivity rises sharply with an increase in the absolute gate voltage, and the changes in sign at the gate voltage of about 0 volt. Figure 3D shows the photoresponsivity of the 3D GFETs can be enhanced by application of source drain bias voltage, but the fluctuations also increase because of the enhanced dark current that occurs in the graphene. Figure 3e shows the electrical field magnitude distribution near 3D GFET with only one roll-up winding. Under illumination by normal incident light at the wavelength of 540 nanometer and an electrical field of magnitude of E0, 1 volt per meter. Figure 3f shows the optical field over the range from the ultraviolet region to the visible region. As the incident light wavelength increases from 300 to 1000 nanometer, the E3D and E0 decreases before 900 nanometer and then increases slightly. The higher electric field magnitude at the 3D graphene surface allows more energy to be absorbed, which then leads to higher photoresponsivity. Next, we will look into the figure 4, which is photoresponses of the 3D GFETs in mid-infrared and terahertz regions. Figure 4a shows the experimental setup of 3D GFETs which tested under both mid-infrared 10.6 micrometer and terahertz 2.52 terahertz and 3.11 terahertz illuminations. Figure 4b shows a typical on-off photocurrent characteristic of a 3D GFET under illumination by an incident laser of 119 micrometer power on the GFET 3D GFET of 12.8 microwatt. After hundreds of on-off cycles, the photocurrent level is maintained well, thus indicating the good reliability and reversibility of the 3D GFETs. Figure 4c shows a plot of a power dependence of the photocurrent for 3D GFETs with different numbers of roll-up windings. Based on the 3D GFET with only one winding, a photoresponsivity of 1.9 milliampere per watt was obtained at the wavelength of 119 micrometer. When the number of windings of 3D GFETs was increased from 1 to 2, the photoresponsivity then also increased to 15.7 milliamp per watt. When the number of windings increases continuously to 5, achieve photoresponsivity of 113.2 milliamp per watt as shown in figure 4c. Figure 4d and E shows the performance of 5 windings of 3D GFETs. Photoresponsivity of 16.4 and 232.8 milliampere per watt were obtained at wavelengths of 10.6 and 96 micrometer respectively. This data 232.8 and milliamp per watt occurs at 3.11 terahertz, which is 7th order of the magnitude higher than the 5 nanoamp per watt obtained for 2D single layer graphene. Figure 4f shows the voltage photoresponsivity of the 3D GFETs was 28.9 volt per watt at 3.11 terahertz under zero gate bias conditions. Next, we look figure 5, which describes high speed photoresponse of the 3D GFETs via impulse response measurements. Okay, figure 5a as shown on the left shows the rise and the fall time are defined as the signal increases and decreases from 10% and 90% to 90% and 10% of the stable signal respectively. From the impulse response of the 3D GFET photodetector, the rise time TR and the fall time TF are 265 and 220 nanoseconds respectively. Figure 5G as shown below shows a discrete time Fourier transform of the time domain data provided the spectrum of the 3D GFET photodetector. The 3 dB bandwidth of the 3D GFET photodetector is 1.38 MHz. Electrical bandwidth obtained is approximately the bandwidth of the measurement system. Anticipate that these 3D GFET photodetectors may also work at even higher frequencies. Okay. Table 1, which is from the Journal 2, it summarizes the reported high performance photodetectors based on graphene and other two-dimensional 2D materials. Even though the 3D GFAT photodetectors do not have the highest responsivity, the highest detectivity, the lowest NEP, or the fastest response speed, they have the broadest operation wavelength range and good comprehensive performance. Next, the third journal, which is the Broadband Black-Phosphorus photodetector with high responsivity. The summary of this paper. In this paper, researchers have demonstrated a high-performance broadband Black-Phosphorus based photodetector in the wavelength range from 400 to 900 nanometer. The broadband photodetectors reported here are based on black gate field effect transistor (FET) configuration. A systematic study of the photoresponse dependence on the temperature, incident laser power density, photon energy, and channel length of broadband-based photodetector is carried out for the first time. These performance parameters are among the best in the 2D materials-based photodetector reported so far, showing the great potential of Black-Phosphorus in the application of broadband photodetection at a wide temperature range. Next, we look into the research methodology of this paper. First, a few black layer phosphorus was exfoliated and identified under optical microscope. Next will be deposition of black phosphorus aluminum method by electron beam lithography. Third process will be characterization and determine the thickness of black phosphorus flakes. This is to measure the topography and the number of black phosphorus layer. This was done under atomic force microscopy (AFM). The next process, the device was placed in the electrical shield and optically seed probe station system under optronics characterization. Then the 3D adjustable optical fiber for laser guide a tunable TI sapphire laser system into the device. This is to 3D adjustable is a 3D adjustable optical fiber. Then mounts the photon generator in tunable TI sapphire laser or harmonic generator to perform electrical characterization. Next, we'll look into the result and discussion for the broadband black phosphorus photodetector with high responsivity. Figure 1 shows the schematic views of devices. Figure 1a, as shown on the left, shows the broadband photodetectors reported are based on gate field effect transistor (FET) configuration. Few layer broadband flakes are obtained using mechanical exfoliation into a 90 nanometer silicon oxide substrate. The source or drain electrodes were patterned by electron beam (e-beam lithography), and nickel or aluminum metal contact was deposited by e-beam evaporation. Figure 1b shows the atomic force microscopy (AFM) images. The thickness of broadband phosphorus flake is measured to be 8 nanometer, corresponding to the 15 layers as depicted in Figure 1d as below. Figure 1c shows the Raman spectrum where the 3 Raman peaks at 362.2, 439.8 and 467.6 per centimeter. Next slide. This slide shows the electronic and optoelectronic characteristics of the 1 micrometer device. Figure 2a and b shows the output characteristic of the 1 micrometer broadband FET in dark and under illumination measured at 300K and 200K. Observe that the photocurrent generated increases when the gate bias and drain bias increases. Photocurrent also increases when the temperature is reduced to 20K. Figure 2c and 2d shows the illustration characterize the photocurrent dependence on gate bias and drain bias at different temperatures. It can be seen that the photo response increases gently at low temperature. Figure 3 shows the photoresponse of the same 1 micrometer device. Figure 3a as shown on left, the photoresponse of the same micrometer device with different incident laser power density as it decreases from 250 milliwatt per centimeter square down to 50 microwatt per centimeter square at 633 nanometer wavelength, which measured at 320 K. Observe the photocurrent increases with increasing laser power, and moreover, distinct photocurrent can be observed even at lowest power density of 50 microwatt centimeter square at 20 K. Figure 3b and c shows the two representative wavelengths at 633 and 900 nanometer are used and the corresponding are. At room temperature, it shows very strong photoresponse to the incident photons from the visible to near infrared spectrum. A high photoresponsivity, which is R equals to 6.7 times 10 to the power of 5 ampere per watt for 633 nanometer, which can be achieved. While near the infrared region of 900 nanometer, a high responsivity about 10 to the power of 3 ampere per watt at 300 K and 7 to the power of 6 ampere per watt at 20 K has been achieved for the first time. Figure 3D summarizes the external quantum efficiencies, shows an increasing trend from 900 to 400 nanometer, which can be attributed to the increased photon energy as shown in figure 3D. Figure 4, it shows the length and scaling dependence on the photoresponse. Figure 4a shows the photoresponse is asymmetrical behavior where the photocurrent only exists in the p-type FET. Figure 4b will further explore the mechanism of the asymmetry. Venn diagrams of the device under both types of operations are illustrated in the figure. The photo-induced carriers can be easily generated at both P branch and N branch without distinction. During the transport and collection, the Scotchy barrier height is much higher in the N-type region and makes it more difficult for electrons to travel from the source end. As a result, the photocurrent is strongly surpassed in the N branch, which also explains the minimal photocurrent in the off state. Figure 4c plots shows the photocurrents of various devices with different channel lengths are measured at 300 and 200 K, and as channel length decreases, the photocurrent increases mainly due to the larger transverse electric field and smaller transit time. Figure 4D shows a 100 nanometer device shows a record high R of 4.3 to the power of 6 ampere per watt at 300 K, which is 2 orders of magnitude higher than that of 1 micrometer device. Next slide will explain the overall comparisons of the research papers. Journal 1, which is high performance self-powered photodetectors based on perovskite and graphene. The novelty, a self-powered photodetector in which multi-layer graphene is used as an efficient pathway for photocarriers and perovskite as the photodetective layers. The devices are prepared by transferring the graphene electrode onto a TiO2 F-doped silicon oxide FTO substrate to form a Scotchy junction between graphene and tin oxide. The perovskite layer is spin coated on the graphene as a photoactive layer for light absorption. The second journal, which is three-dimensional graphene field effect transistor as high-performance photodetectors, researchers have demonstrated a self-rolled-up 3D GFET photodetectors to balance its photoresponsivity, spectral range, and electrical bandwidth. Journal 3, which is a broadband Black-Phosphorus photodetector with high responsivity, researchers have demonstrated a high-performance broadband photodetectors with photoresponsivity in a broad range from 400 to 900 nanometer, as well as a quantitative analysis photoresponse at different temperature from 300 down to 20K. The broadband phosphorus photodetectors reported here are based on black gate field effect transistor, which is FET. Next, we look into the methods comparison of methods used in each journal. Journal 1. The method they have used is annealing, CVD, spin coating, and UV zone. If you look at the annealing, they have performed a method at low temperature solution procedure whereby a 40 nanometer tin oxide deposited onto FTO by using low temperature procedure. Next, the annealing temperature of 200, 300, and 550, which is done by cleaning the deposited substrate with deionized water and perform annealing. The third method is to form a dark perovskite film which annealed at temperature of 100 degrees Celsius for 10 minutes. The CVD method, chemical vapor deposition, whereby to form a multilayer graphene transfer into tin oxide. There are two spin coating process has been done in the first journal for perovskite solution coated on tin oxide, and also PTA solution with perovskite solution coating process. Then we have done a UV zone method, which is an interval of 1 minute, 2 minute, 3 minute, which to treat the opposite side of the film. If you look at the journal 2, CVD process, whereby they have used a plasma enhanced chemical vapor deposition method for aluminum layer deposition on silicon tensile strain silicon nitride layer. They also use a plasma etching method, whereby the CVD grown graphene was transferred onto a silicon oxide layer and patterned using oxygen plasma etching. Third method will be spin coating process for the 3D GFET characterization, and then the sputtering process technique for the deposition of chromium or aluminum gate electrode structure to sputter on the silicon nitride layer about 30 nanometer thick. The third journal only uses a electron beam lithography for the deposition process for nickel and gold. Next, we will look into the analysis and result comparison of the three journals. The wavelength performed in the journals for the first journal will be about 260 nanometer to 900 nanometer. Second journal will be at the UV, visible, MIR, and terahertz. The third journal will be 400 nanometer to 900 nanometer. The responsivity for the first journal is 0.375 ampere per watt. Second journal, which is more than 1 for UV and visible, and about 0.23 for 96 micrometer. The third journal shows 7 to the power of 6 ampere per watt for 20K at 100 nanometer, and 4.3 power of 6 ampere per watt at 300K for 100 nanometer. Next, we will look into the overall conclusion of the three journals. The first journal shows the high-performance self-powered photodetectors based on perovskite and graphene. This paper summarizes the self-powered photodetector, which graphene as an electrode and perovskite as the active material was developed for the first time, which demonstrate a good responsivity and high specific detectivity. The high performance is attributed to the combination of graphene and perovskite, that is, the high mobility and conductivity of graphene combined with the strong and broadband light absorption of perovskite. This study provides a promising method for the development of high-performance self-powered photodetectors that have a simple structure. This paper could provide a platform for changing the perovskite layer with a thin base photoactive layer with mid-infrared light absorption for infrared detection. The second genre, which is a three-dimensional graphene field effect transistor as high-performance photodetector. In this paper, as a conclusion, the self-rolled up 3D GFET can be used as a high-performance photodetector that have a high photo responsivity, broad spectral range, and high operating speed simultaneously. To promote further improvement in device performance, high-quality graphene and asymmetrical electrode structure should be used. The fabrication technique proposed in this paper can also be transferred to enable the fabrication of 3D photoelectronic devices and systems based on also Black-Phosphorus and also graphene-like 2D materials. The summary of the third paper, Broadband Black-Phosphorus photodetector with high responsivity. As a conclusion, high-performance broadband Black-Phosphorus based photodetector demonstrate, which is in the wavelength range from 400 to 900 nanometer. The record high photoresponsivity reaches up to 7 power of 6 ampere per watt at 20K and 4.3 to power of 6 ampere per watt at 300K for 100 nanometer devices in the broadband spectrum. A systematic study of the photoresponse dependence on the temperature, incident laser power density, photon energy, and channel length of Black-Phosphorus based photodetectors is carried out for the first time. These performance parameters are among the best in the 2D materials based photodetectors reported so far, showing a great potential of Black-Phosphorus in the application of broadband photodetection at the wide temperature range. Okay, a summary. My preferred journal will be Broadband Black-Phosphorus photodetector with high responsivity. Black-Phosphorus is an elemental 2D semiconducting material with direct bandgap of around 1.5 eV for monolayer and down to 0.3 eV in bulk. Such a narrow bandgap covering the spectral range from visible to near infrared makes Black-Phosphorus a very promising candidate for broadband optoelectronic applications. In addition to the higher carrier mobility, few layer Black-Phosphorus has a direct bandgap and strong light absorption efficiency in broadband spectrum, of all which are crucial factors for high-performance photodetection. Responsivity shows broadband Black-Phosphorus photodetector has the highest, whereby 7 times 10 to the power 6 ampere per watt at 20K of 100 nanometer and 4.3 times 10 to the power 6 ampere per watt at 300K of 100 nanometer compared to the first journal, the second journal, three-dimensional graphene field effect transition as high-performance photodetector, and the first journal, high-performance self-powered photodetectors based on perovskite graphene, whereby the responsivities of about 1 ampere per watt for UV and visible light and 0.375 ampere per watt respectively. Thank you very much.